Have you ever really sat down and thought about infinity? I mean, as someone who thinks about the really big questions, existence, knowledge, all that, you've probably bumped into the idea of infinity at some point, right? And it's kind of a paradox, isn't it? Boundless, yet a concept we try to grasp. Today we're diving into a fascinating chapter of, well, intellectual history, where these big philosophical questions about infinity get, I don't know, a bit more rigorous. We're talking about the early days of set theory.
Exactly. It might seem like just a technical area within math,
Mhm.
just studying collections of things, but it really sparked a revolution in how mathematicians think about the very objects they're working with. It made them confront these really deep questions about existence, identity, even infinity itself.
And that's exactly what we're going to unpack today. Not just set theory as some mathematical tool, but as this fundamental shift in thinking, a new way of seeing mathematical objects. And our guide on this journey, the really thorough entries in the Stanford Encyclopedia of Philosophy. So we're on solid ground here.
Absolutely. Our goal in this deep dive is to see how this seemingly simple idea, this set, just a bunch of distinct things, evolved into a cornerstone of modern math.
Hmm.
And it wasn't a smooth process, oh no. It involved wrestling with some truly mind-bending paradoxes. But those struggles ultimately gave us these profound insights into infinity and even the very structure of mathematical thought. And I think this is going to resonate with you, our philosopher listener.
Totally. Think of it like a philosophical drama playing out on the stage of math with these intellectual giants like Cantor, Dedekind, Zermelo. They're the stars. And their breakthroughs, their struggles, those weren't just calculations. They were like deep engagements with the most fundamental ideas. So let's rewind. Where does this whole mathematical exploration of infinity actually begin?
Well, there's this misconception that, before George Cantor came along, everyone was just like, nope, no actual infinity, thank you very much. But that's not quite true. Thinkers like Bolzano, Riemann, Dedekind, they had already accepted the concept of infinity as this complete totality.
Yeah.
They weren't afraid of it. They were starting to explore it.
So Cantor wasn't this lone warrior fighting against a math establishment terrified of infinity.
Not quite. He faced some pushback, sure, but the seeds for accepting actual infinity had already been planted. It's also important to note that set theory didn't just pop up from analysis, the study of continuous change. Its roots are much broader. Algebra, number theory, geometry, they all played a role. And those initial set theoretic concepts, they were already starting to sprout even before Cantor's most famous works.
So what was the big shift, the conceptual leap that got things rolling?
It was the transition from thinking about just collections or logical classes, things grouped together by some shared property, to the modern idea of a set as a mathematical object, like its own thing with its own identity,
Yeah.
something you could manipulate and relate to other sets. Bertrand Russell later made this distinction clear. He talked about classes many for the individual elements and classes one for the set as a single entity. Think of it like a bunch of trees, right? That's many. But the forest, that's one, a single concept.
Oh, I see. It's not just a list of members, it's an entity itself. That seems like a huge change.
Absolutely. The logical idea of a concept extension, gathering all things that fit under a concept, that was a starting point. But the focus there was on the concept, not the individual things. So mathematicians made two big changes. One, they started looking at collections of specific things, not just concepts. And two, they went for absolute generality, no more predefined conceptual boundaries.
So logic gave them some tools, but they took those tools and really ran with them.
Exactly. Even Zermelo himself credited Cantor and Dedekind with set theory's creation. And looking back, Bolzano and Riemann, they were really important precursors, even though Bolzano's impact was limited by the math of his time.
Bolzano, wasn't he the one who got into the paradoxes of infinity?
That's him. He was way ahead of his time, exploring paradoxes in infinity. He even understood this idea of one-to-one correspondence between infinite sets. Like you can pair up each point in a line segment of length 1 with every point in a line segment twice as long, right? Suggesting some kind of equivalence in their infinitude.
But he stopped short of this concept of cardinality, probably stuck on those traditional ideas of size and measurement.
He saw the pairing, the structural similarity in their infinity, but hesitated to say they had the same size abstractly.
Exactly. It seems that the idea of metric concepts, distance, measurement, all that, they kind of held him back. It took fields like projective geometry and especially topology, which focus on shapes and connections, not measurement, to really break free from those constraints and open up the way for this abstract approach to sets.
And Riemann, with his groundbreaking work on geometry, he played a part in this liberation too, right? Oh, absolutely. He was crucial. In his famous lecture on the foundations of geometry, Riemann imagined building all of math on the idea of a set, or a manifold, as he called it. He also pushed for this super conceptual math, where the ideas, the relationships, those are the stars, not just the formulas. Like, he accepted Dirichlet's very general view of a function, any correspondence between numbers, whether you have a formula for it or not. This emphasis on abstract structure deeply influenced both Dedekind and Cantor.
Sounds like Raymond planted some seriously influential seeds.
He did. And between 1868 and 1872, there was this incredible surge of set theoretic ideas in Germany, like a big bang. Dedekind published Raymond's geometry lecture and some other important work of his in 1868. It sparked a ton of activity in real analysis, studying discontinuous functions. And that's where Cantor steps onto the scene, initially focusing on sets of points on the real line. By 1872, he was already thinking about doing an operation on a set, infinitely many times his first glimpse into the transfinite.
So Cantor's journey into infinity started with real numbers, not abstract ideas.
Exactly. But at the same time, Richard Dedekind was independently developing set theoretic ideas in a more abstract area, algebraic number theory. Around 1871, he was defining fields and ideals using set theoretic language. He used set operations and mappings that preserve structure. His work was incredibly precise, dealing with equivalence relations, set partitions, homomorphisms, automorphisms. So many of the tools and ways of thinking we use today came from his work. He even published a clear and concise presentation of basic set theory in 1888, formalizing the operations he'd been using for years.
It's amazing how these foundational concepts were popping up at the same time in different places.
And Dedekind wasn't done. In 1872, same year Cantor's dipping his toes into the transfinite, Dedekind gave us this rigorous axiomatic analysis of real numbers. He defined them as a complete ordered field using his Dedekind cuts. This was a different approach from Cantor, who used Cauchy sequences, and from Weierstrass, who preferred Bolzano's principle of nested intervals.
But all these different ways of defining real numbers, they shared some deeper assumptions about sets and infinity, right?
You got it. Looking back, both Dedekind and Cantor relied on this power set principle, the idea that for any set, you can have the set of all its subsets. They both started with a set of rational numbers and built up the reals from infinite sets of those rationals. And this is where Kronecker started his constructivist critique. He questioned these infinite processes that seem to just conjure up mathematical objects without a clear way to construct them.
And amidst all this foundational work, Cantor makes his huge discovery about different sizes of infinity.
Yep, late 1873. Through letters with Dedekind, he was wrestling with this. Could you match up the natural numbers with the real numbers one-to-one? Dedekind had actually proved you could do that with algebraic numbers, roots of polynomials with integer coefficients. But just days later, Cantor made a breakthrough. He proved that the reals can't be matched up one-to-one with the naturals. He used the Bolzano-Weierstrass principle, showed that assuming a correspondence leads to a contradiction.
So that was the moment mathematicians realized infinity wasn't just one thing, but came in different magnitudes.
Absolutely. The cardinality of the reals was bigger than that of the naturals, the rationals, even the algebraic numbers. This was huge. Changed how people understood numbers and infinity itself.
And this all went into his 1874 paper, The Birth of Transfinite Set Theory. Although it sounds like there was some drama with Dedekind in the publication.
Oh, yeah, there was. Cantor used Dedekind's ideas, even quoted their letters in the paper, caused some tension between them. Ethical questions we're still debating today. But drama aside, the second theorem in that paper, Cantor's own proof that the reals are uncountable, that was revolutionary.
All right, so we've seen the spark, the emergence of these radical new ideas. But what about the consolidation? How did this turn into a more solid framework?
Well, even though Cantor's 1874 paper was groundbreaking, set theory didn't just take over immediately. Dedekind's more algebraic approach to foundations didn't really catch on to the 1890s when people like David Hilbert started championing it. The theory of real functions became like this testing ground for these new ideas, with mathematicians all over Italy, Germany, France, Britain contributing a ton. Thinkers like Peano, Frege, later Russell, they also picked up these set theoretic ideas and used them in their work on logic and the foundations of math.
But Cantor was still driving the field forward, right?
For sure. Between 1878 and 1885, he published a bunch of crucial work that really solidified set theory as its own field. He gave us the notation A equivalent to B to say two sets have the same cardinality, meaning they can be matched up one-to-one. He showed some surprising equivalences, like the irrationals have the same cardinality as all the reals, and even that n-dimensional space has the same cardinality as the one-dimensional real line. And then, in 1878, he formulated his famous continuum hypothesis.
The one about the cardinality of subsets of the reals, right?
Yeah, the first, weakest form of it. It basically said any infinite subset of the reals is either countable, same cardinality as the naturals, a Lafont, or it has the cardinality of the continuum, the reals themselves. And over the next few years, Cantor dove deep into the topological properties of sets of points on the real line. He introduced concepts like closed sets, those containing all their limit points, and perfect sets, closed sets with no isolated points. This led to his important Cantor-Bendixson theorem.
Closed and perfect sets. Those seem pretty crucial for understanding the real line from a set theory perspective.
They are. So a set P is closed if its set of limit points, P prime, is a subset of P. And a perfect set is a closed set where every point is a limit point. The Cantor-Bendixson theorem basically says any closed set can be uniquely split into a countable set and a perfect set. This implies that closed sets have the perfect set property. If a closed set is uncountable, it has to have a perfect subset. And Cantor himself proved in 1884 that all perfect sets have the power of the continuum, supporting his continuum hypothesis for those sets. Later, this was extended to Borel sets by people like Alexandrov and Hausdorff in 1916.
So Cantor was really making headway using set theory to understand the real number line.
He was. But then, 1882, a pivotal moment. He started thinking about transfinite numbers in a more abstract way, not tied to point sets. There was a big shift for set theory toward a more abstract, axiomatic approach. It became about the properties of infinite sets in general, not just subsets of the reals. He focused on transfinite cardinals, the size of infinite sets, and transfinite ordinals, which capture the order type of well-ordered sets.
And the transfinite ordinals, those were his way of grappling with these new infinite numbers.
Exactly. He introduced them in his 1883 work, Grundlagen, using two principles. 1, the successor principle, add 1 to an ordinal to get the next, and 2, the limit principle, there's an ordinal after any infinite sequence of ordinals with no last element. This let him build the transfinite ordinals, omega the first infinite one, then omega plus 1, omega plus 2, and so on, omega times 2, omega times 3, omega squared, a whole hierarchy. Many of his peers were skeptical of these new numbers, but Cantor was convinced they were key to understanding infinity.
And from these transfinite ordinals, he got his alephs, his hierarchy of infinities.
Exactly. He grouped ordinals into number classes. The first class was all the finite ones, 0, 1, 2, and so on. The second class started with omega and included all the ordinals with only countably many predecessors. That condition, countably many predecessors, that was key. Cantor showed that the cardinality of the second class was strictly bigger than that of the natural numbers, Aleph null, and there was no cardinality in between. He called the cardinality of that second class Aleph 1.
So the alephs, Aleph null, Aleph 1, Aleph 2, and so on, they came from this classification of ordinals by size.
Yep. Each number class, third, fourth, and so on, had a cardinality bigger than the one before it. That's how he got his famous scale of increasing transfinite cardinalities. Aleph null, Aleph 1, Aleph 2, and so on. This let him restate the continuum hypothesis more precisely. The cardinality of the continuum, the real numbers, is Aleph 1, the smallest uncountable cardinality. He even used transfinite ordinals to give a more rigorous proof of his earlier Cantor-Bendixson theorem.
It sounds like the idea of order, how things are arranged in a set, became really important for Cantor.
It did. Studying transfinite ordinals led him to think about ordered sets, especially well-ordered sets, where every non-empty subset has a least element, like the natural numbers with their usual order. But the reals, they're not well-ordered in their standard order. Think about all the positive reals, no least element there.
And he saw these transfinite ordinals as representing the unique type of order of well-ordered sets.
Precisely. Each ordinal represented a distinct way a well-ordered set could be arranged, its order type. He even showed you could take the naturals, order type omega, and rearrange them to have different order types, like omega times three copies of the naturals, one after the other. This deep link between ordinals and ordering led him to believe that the reals, and actually any set, could be well-ordered somehow, even if we can't actually describe the ordering. He called this the well-ordering principle and considered it a fundamental law of thought. Years later, David Hilbert put the continuum hypothesis and the well-ordering problem on his famous list of the biggest open questions in math at the 1900 International Congress.
So by the late 1890s, Cantor had built this elaborate world of transfinite numbers and well-ordered sets. But it seems his final publications didn't capture everything or address all the questions that were coming up.
True. His final publications in 1895 and 1897 in Mathematician Annalen were a big overview of his transfinite number theory and well-ordered sets. but they didn't really have any groundbreaking new ideas. Interestingly, he didn't include this planned third part that would have dealt with the paradoxes that were popping up in his thoughts on well ordering. And he also left out a formal statement and proof of Cantor's theorem, the one that says the power set of a set is always bigger than the set itself. He published that in 1892. He also didn't include his elegant diagonal argument for the uncountability of the reals, even though he published that earlier, and it was clearly connected to work by Paul du Bois-Reymond on orders of infinity.
It sounds like the paradoxes were already looming large, maybe influencing what he chose to include. But before we get into that, we should mention that Dedekind was making some fundamental contributions around this time too, right? Especially with natural numbers.
Oh yeah, absolutely. His 1888 work, Was sind und was sollen Diskel, was a landmark for the foundations of arithmetic. He gave a rigorous axiomatic system for the natural numbers, using the concept of a function and a special element, 1/10. He meticulously proved mathematical induction and the validity of recursive definitions, systematically developed basic arithmetic, and, crucially, showed his system was categorical. That means it uniquely characterizes the natural numbers up to isomorphism. Any two models of his axioms are essentially the same. The key was the minimality condition in his axioms. He also developed a general theory of chains of sets under mappings, which was key to his beautiful proof of the Cantor-Bernstein theorem.
And this axiomatic approach was catching on more broadly in math, wasn't it?
It was. At the same time, people like Peano and Frege were working on formalizing the naturals in arithmetic using logic. And Hilbert's very influential book, Grundlagen der Geometrie, published in 1899, that was heavily inspired by set theoretic thinking. It really pushed the axiomatic method as a core part of modern math.
But not everyone was thrilled about these new infinitary methods and this abstract approach to foundations, right? There was some pushback.
Oh, definitely. From the beginning, people like Kronecker were criticizing Cantor's work from a constructivist perspective. They rejected the completed infinity as a legitimate object and wanted math to be based on constructive methods. And later, thinkers like Brouwer and even Wittgenstein echoed those concerns. Even Weierstrass, a giant in analysis, initially objected to Cantor's idea of different sizes of infinity. Throughout the early 20th century, quite a few mathematicians, Borel, Poincaré, Wales, Skolem, they all had doubts about the consistency and validity of set theory's foundations. Wittgenstein even went so far as to call it nonsense.
So a lot of discovering consolidation, but also growing unease. And that brings us to the crisis period when those paradoxes really started shaking things up.
Exactly. By the late 19th century, the goal of arithmetization, grounding all of math and arithmetic that morphed into grounding everything in set theory, thanks to Cantor and Dedekind. But just as people were celebrating this new unified foundation, the ground started shaking. Paradoxes started popping up within set theory itself.
And Cantor was among the first to find these contradictions.
Yeah, it's kind of remarkable. His work on transfinite numbers led him to the Burali-Forti paradox. That's the one about ordinals. If you take the collection of all ordinal numbers, and it's a set, it should have its own ordinal number, representing its order type. But then that ordinal should be bigger than every other ordinal in the collection, meaning bigger than itself. It's not clear exactly when Cantor discovered this paradox, but most likely sometime in the mid-1890s.
That's a wild contradiction. An order type that's both part of the collection of all order types and also bigger than all of them.
I know. And around the same time, Cantor also found the Cantor paradox, sometimes called the paradox of the alephs or the paradox of the largest cardinal. This one comes from applying Cantor's own theorem, the one about the power set always being bigger, to the hypothetical set of all cardinal numbers. If this set existed, its power set would be bigger, meaning there's a cardinal bigger than the biggest cardinal. Cantor realized these paradoxes were a real problem for the foundations people like Frege and Dedekind were building. He even said in his letters that his own views on collections were diametrically opposed to Dedekind's assumption that all well-defined collections were consistent systems.
So Cantor tried to solve this by saying there are consistent multiplicities, the sets, and inconsistent multiplicities, the collections that are just too big to be sets.
He did try that, but he never gave any clear rules for how to tell them apart. So it was more of a label than a solution. He knew these were big problems and decided not to publish that planned third part of his big papers in Mathematische Annalen. That part was going to be about paradoxes and well-ordering, but his letters tell us what he was thinking. Interestingly, in some of his unpublished notes, he tried to use the Burali-Forti paradox to argue that every set can be well-ordered, but that argument depended on this fuzzy idea of inconsistent multiplicities.
It seems these paradoxes really shook the foundations of math, made everyone question what even counts as a mathematical object.
They did. Even Hilbert formulated his own paradox, and Zermelo, completely independent of Russell, discovered what we now call Russell's paradox, the one about the set of all sets that don't contain themselves. Bertrand Russell also came up with it independently, inspired by Cantor's theorem and his own early belief in a universal set.
Ah, yes. The famous R equals the set of all, such that X is not an element of X. If R is a set, we're in trouble. If R contains itself, it shouldn't, and if it doesn't, it should. It's a real logical knot.
It is. And Russell wrote about this contradiction to Frege in 1902, right when Frege was finishing his big book, Grundgesetz, which was meant to be the logical foundation for all of arithmetic. Frege was devastated. He realized this paradox completely wrecked his project. In a heartbreaking addendum to his book, he said, "A scientist can hardly encounter anything more undesirable than to have the foundation shaken just as the work is finished. I have been put in this position by a letter from Mr. Bertrand Russell." He couldn't see how arithmetic could be truly solid if basic logic led to these contradictions.
Frege's Grundgesetz and Russell's own principles of mathematics really brought these foundational problems into the spotlight.
They did. They made everyone aware of these paradoxes and how serious they were. Even people like Hilbert and Zermelo might not have fully grasped the situation until Russell's paradox came along. What made it so bad was that it used such simple ideas, negation, the not, an X not an X, and set membership. Those were considered purely logical. It challenged the principle of unrestricted comprehension, the idea that for any property, there's a set of all the things that have that property.
So how did everyone try to deal with this crisis? What were some of the early reactions and solutions?
It was a mixed bag. Cantor, who had this more philosophical side, he was leaning towards rejecting the whole idea of a universal set, the set of everything. Frege and Russell, in their early attempts to build logicist foundations, they had basically relied on unrestricted comprehension, which we now know is a problem. Dedekind was a bit more careful about unrestricted comprehension, but he still seemed to assume there was an absolute universe, some ultimate collection, and he was fine with making any subset of that universe.
This idea of arbitrary subsets seems to have been really important for both Cantor and Dedekind, even if they didn't always examine it too closely.
For sure. It was this deep intuition for both of them, probably influenced by the Dirichlet-Riemann tradition in analysis, where arbitrary functions were okay, any correspondence, even without a formula, was a function. It's interesting that this iterative view of sets, where you build sets up in stages from simpler sets, wasn't really a big part of their foundational thinking. Cantor, for example, he often thought of sets as collections of similar elements within a specific conceptual sphere. This iterative view of sets was more fully developed later by Gödel, based on work by von Neumann and Zermelo.
So no easy answers. And it wasn't just set theory with paradoxes, right? Logic and semantics had their own problems, too.
Absolutely. Alongside the set theory paradoxes, we had a whole bunch of logical or semantic paradoxes. Russell's Barber paradox, Richard's paradox about definability, Koenig's paradox about the smallest undefinable ordinal, Berry's paradox about the shortest description of a number, the Grelling-Nelson paradox with those self-referential adjectives, and the classic liar paradox. This statement is false. And the solutions people proposed for these paradoxes were all over the place. Russell developed his famous ramified type theory, which he presented in Principia Mathematica with Whitehead, to try and resolve all the paradoxes by organizing logical types into a hierarchy. Zermelo, on the other hand, thought most of the paradoxes would just go away if you had a carefully designed axiomatic system for set theory that limited comprehension.
And in the middle of all this, you've got the debates about the continuum hypothesis and well-ordering, those big questions Hilbert highlighted, still going strong.
Yep. At the 1904 International Congress of Mathematicians, Julius Koenig presented what he thought was a proof that the cardinality of the continuum couldn't be any of Cantor's Alephs. His argument relied on a result by Bernstein, but that result had a gap. Hausdorff later fixed Bernstein's result and corrected Koenig's theorem, showing it did put a real constraint on the continuum problem. Specifically, it said the cardinality of the continuum can't be Aleph omega.
So even trying to solve those big open problems was tricky because of the foundational issues. And then in that same year, Zermelo gives his proof of the well-ordering theorem, but it used the controversial axiom of choice.
It did. He showed that any set could be well-ordered, meaning you can order it so every subset has a least element. But his proof needed the axiom of choice, which says you can pick an element from each set in a collection of non-empty sets, even if there are infinitely many and you don't have a rule for picking. And that axiom caused a big, sometimes heated, debate.
It's kind of ironic, isn't it? This axiom, which basically says you can make arbitrary subsets by making infinite choices, people had a problem with it, even though arbitrary subsets were so central to Cantor and Dedekind's thinking.
It really is. A lot of big mathematicians at the time, like Russell, Weil, and Brouwer, were really suspicious of the axiom of choice, mainly because it wasn't constructive. It just says the choice function exists, but it doesn't tell you how to define it. And even though it was really useful in analysis, it had some strained consequences, like the Banach-Tarski paradox, where you can supposedly split a sphere into pieces and rearrange them into two spheres the same size as the original. That made people even more skeptical. And the axiom also seemed to say there were sets you couldn't actually construct or define. For a long time, mathematicians would always explicitly say when they were using the axiom of choice in their proofs. That only started to change after Gödel proved in the 1930s that the axiom of choice is relatively consistent with the other axioms of set theory. If Zermelo-Fraenkel's set theory without choice is consistent, then adding choice doesn't make it inconsistent.
So Zermelo responded to the paradoxes and the controversy over his well-ordering theorem by creating a more formal, restricted system, axiomatic set theory.
Yes. In 1908, he published his system of axioms. It was carefully designed to avoid the known paradoxes by limiting how you can form sets. It was still strong enough to develop Cantor's theory of cardinals and ordinals, but in a much more controlled way. If you want to really dive into Zermelo's axioms and what they mean, you can check out the relevant entries on Zermelo's axiomatization.
Okay, so we've gone from those initial discoveries to the paradoxes, and now to a more formal axiomatic system. What happened in the field between Zermelo and Gödel's work in the 1930s?
During that time, roughly 1900 to 1930, it's important to note that set theory still meant different things to different people. For a lot of mathematicians, it still included things like topology and functions of real variables, even though folks like Cantor, Dedekind, and Zermelo were more focused on the abstract, foundational side of pure set theory. At the first International Congress of Mathematicians in 1897, mathematicians like Hadamard and Hurwitz even defended set theory by saying how important it was for analysis.
And this connection to analysis was important for the development of descriptive set theory, right?
Yeah, right around 1900, motivated by questions in analysis, descriptive set theory, or DST, popped up. It was mainly developed by people like Borel, Baire, and Lebesgue. Their work extended Cantor's earlier work on definable sets of real numbers, where he had shown that the continuum hypothesis holds for closed sets. They developed a whole hierarchy of Borel sets, starting with open sets and using countable unions and complements. Lebesgue's work on measure theory in 1905 gave them more tools. He showed that the hierarchy of Borel sets goes through all the countable ordinals and connected them to Baire functions. The main goal of DST was to uncover the properties of these definable sets of reals, like the perfect set property. If it's uncountable, it's got a perfect subset, which means the continuum hypothesis holds for that set, and regularity properties like Lebesgue measurability and the Baire property being almost open. In 1916, Hausdorff and Alexandrov proved that all Borel sets have the perfect set property.
So descriptive set theory was about getting a really detailed understanding of the real line by classifying and studying its well-behaved subsets.
Exactly. After Borel sets, they moved on to analytic sets, which are continuous images or projections of Borel sets. Luzin and Alexandrov did a lot of work there. Suslin made a key discovery in 1917 when he showed that analytic sets aren't always Borel sets. That revealed more complexity in the real line. But he also proved that analytic sets still have the perfect set property, so they satisfy the continuum hypothesis too.
It sounds like they were making progress towards understanding the continuum hypothesis by looking at these increasingly complex sets.
That was the hope. Luzin and Sierpieski then moved on to coanalytic sets, the complements of analytic sets, and developed the projective hierarchy in the 1920s. This was an even bigger classification of sets of reals. It had the analytic sets called sigma 1, 1, coanalytic sets called pi 1, 1, then sigma 1, 2, pi 1, 2, and so on. Sierpieski proved a cool result. Every sigma 1, 2 set is the union of LF1 Borel sets. But around the 1940s, this type of research started to hit a wall.
So this line of research eventually stalled out. What are the signs that things were getting tough?
Luzin and Sierpieski had trouble figuring out if the sets higher up in the projective hierarchy had those nice regularity properties that Borel and analytic sets have. Luzin even wrote in 1925 that it might be impossible to know those regularity properties for projective sets beyond the first level. That kind of foreshadowed later developments and raises some really interesting philosophical questions about how much we can really know about the continuum. It's interesting to think about this idea of unknowability in relation to things like projective determinacy, a powerful axiom that came later, and the debates about the evidence for such strong axioms. Lusen's 1930 book, Leçons sur les ensembles énergétiques, became a central text for the field. It's also worth noting that there was a shift in DST towards studying these sets in Baire space, the space of infinite sequences of naturals. Baire space is homeomorphic to the irrationals, and it started to be seen as a more fundamental space for this kind of research.
So even though descriptive set theory told us a lot about definable sets and was tied to analysis and topology, it didn't solve the continuum hypothesis.
It didn't. And we have to remember that Vitali in 1905 had already used the axiom of choice to prove that there are sets of reals that aren't Lebesgue measurable. And Bernstein in 1908 showed that there are uncountable sets with no perfect subset, again using choice. These results suggested that just focusing on well-behaved sets wouldn't be enough to fully understand the continuum. It was Gödel, around 1940, and then the development of forcing by Cohen in the 1960s that really explained why traditional DST research had stalled. They showed that those results by Sussland, Sierpieski, and others were basically as good as you could get within Zeta-Psi Zermelo-Frankel set theory with the axiom of choice. They showed we needed new axioms if we wanted to answer questions like the continuum hypothesis. That was a big part of Gödel's program, looking for those new axioms.
So the focus started to shift from solving these problems within the existing system to actually expanding the system itself. What about Cantor's other big contribution, the theory of transfinite numbers? How did that progress in the early 20th century?
Cantor's ideas about transfinite numbers were super influential. By 1908, Hausdorff had already done a ton of work on uncountable order types, going way beyond Cantor's initial explorations. He introduced the generalized continuum hypothesis, or GCH, which says that 2 to the power of Aleph equals Aleph plus 1 for any ordinal A. He also came up with the idea of weakly inaccessible cardinals. Those are huge infinite cardinal sets.